So here LED, light emitting diode. In this is also PN junction diode only. Everything light emitting diode and then photodiode, solar cell, everything is PN junction diode only. But doping level will be different and then working principle will be different. So here light emitting diode nothing but that is a heavily doped PN junction diode. Only heavily doped will be there. Now here light emitting diode, if you see the LED bulb, smaller LED bulb, how it will be there? Nothing but whenever you see inside of the LED bulb, it will be there like this. Have you observed that? Smaller one, small little one will be there. One terminal will be longer, another will be shorter, like this it will be there. So whenever I connected in the forward bias, it will work in the forward bias only. Whenever I connected in the forward bias, at that time it will give the brightness. Directly you can take the 5 volts battery and then you can connect it, directly it will give the brightness. LED will work directly without any resistor, nothing will be there. So here, what is this working principle? Nothing but I will take the PN junction diode only again. So here P and then N I will take, and then this is a depletion layer, of course, don't go for the transistor again. So this is the depletion layer. Now whenever I connected in the forward bias, then what happens? Generally what happens? Depletion layer will get decreases, right? And also in the junction what happens? There will be more recombination of holes and electrons will be there. Now here whenever I just connected in the forward bias, I said that it is heavily doped. Heavily doped nothing but what will be there? More number of free charge carriers will be there. So more number of free charge carriers are there, immediately I connected to the forward bias. Then what happens? They will gain the energy. Whenever they gain the energy, by that more energy, more number are there. So many number of electrons and then holes are there. So they will move zigzagly and then they will recombine at this whatever the depletion layer we got. Whenever they are recombining here with a higher energy, higher amount of energy, at that time what happens? Nothing but they will release a radiation. So that radiation will be in different forms for the different semiconductors here. So for the few types of semiconductors, that will be that radiation will be in the form of light. So how we will indicate the circuit symbol of that diode means, I will take a PN junction diode only, but what it is giving? It is giving a radiation, so this will be the circuit symbol. It is giving the radiation. So here I said simply the LED nothing but that is a heavily doped PN junction diode. Whenever it is a heavily doped, at that time more number of free charge carriers are available. Whenever I connect in the forward bias, immediately what happens? They will gain the energy. At the depletion layer, there will be more number of recombinations. Whenever it is a less number of recombinations, nothing will happen. Okay, they will move only, then they will produce the current and then little bit of heat will be generated there. The radiation will be in the form of heat. Now what happening here? More number of recombinations are happening. At that time more energy will be released. That energy will be in the form of radiation. For that will be just based on the energy gap of that semiconductor, whichever the semiconductor we have considered. For example, we have taken a semiconductor which is having the energy gap of 1.8 volts to 3 electron volts, 1.8 electron volts to 3 electron volts. Whenever I consider any semiconductors within this limit, they will give the lighting, they will give the brightness as a radiation. Now generally what semiconductors we will use always? Silicon and germanium. What are the values of that? Energy gap values? Silicon is 1.1 and then germanium is 0.7 you will get. So germanium is 0.7, silicon is 1.1. But our limit should be how much here? 1.8 to 3. Can they give lighting? They cannot give lighting. They will give the radiation. That radiation will be in the form of infrared rays. Infrared rays. Infrared rays we cannot see that. So only whenever the radiation is there in the visible region, then only we can feel that radiation. So here the silicon and then germanium diodes will give the infrared radiation. So which diodes will give, which semiconductors will give the light as a radiation? Nothing but there is a gallium arsenic. Gallium arsenic semiconductor give you the light as a radiation. Our silicon and then germanium will give infrared rays as a radiation. See here mainly only one thing is here, the energy here I have to take the heavily doped PN junction diode. In that heavily doped more number of free charge carriers are available. Whenever I connect in the forward bias, what happens? There is more number of electron hole pair recombination will be there. More number of electrons and then holes get paired at the depletion region, and then more number of recombinations are happening, nothing but more energy will be released. That energy will be in the form of what here? Light. That will be in the form of light. Light radiation will be there. So that might be infrared radiation, that might be heat radiation, that might be ultraviolet radiation, anything it might be. But the thing is, which semiconductor you are using is important. For example, if you use the semiconductor which energy gap is in between 1.8 to 3 electron volt, then it will gives you what? Lighting. If not, what happens? Nothing but that will give other radiations. So we know already our germanium and then silicon 1.1 electron volt, germanium 0.7 electron volt. These are not within this limit. So only they will give less radiation as compared to the light. What is that less radiation? Nothing but that is infrared radiation. Okay. In this is everything about the theory. In this, how the problems will be asked means, they will ask the wavelength of the radiated energy. How to calculate that? They will give the energy, initial energy, and then wavelength nothing but E is equals to what is the formula? Hc by lambda, that's it. 2400 electron volts by lambda we will get. To 24,000 re Yuvaraja. 124 12400. Yuvaraja. ಏನು ಯುವರಾಜ ನಿದ್ದೆ ಮಾಡ್ತಾ ಇದೆಯಾ? 12400 ಬೈ ಲ್ಯಾಂಬ್ಡಾ. ಅವ್ರು ಏನು ಅನ್ಕೊಂಡ್ರೆ ಗೊತ್ತಾ? ಓಕೆ, ನಾನು ನಿದ್ದೆ ಮಾಡ್ತಾ ಇದ್ದೀನಿ, ನಾನು ಹೇಳಿದ್ದೀನಿ, ನೀವು ಯಾಕೆ ಬರ್ತೀವಿ ಬೋರ್ಡ್ ಮೇಲೆ? ಸೊ E is equals to 12400 lambda. Lambda will be in terms of what? Armstrongs only. So this is how they will ask the question. And also they will even ask the frequency of the energy radiated. So what is the formula you have to use? E is equals to H into nu you have to use. So this is the problems they can ask based on this LED and all. And also one time they have asked the solar cell graph. Graphs are important in this. So LED will be like normal PN junction diode graph only, it will be there. Okay na? Write that. LED, light emitting diode. Tarun, light emitting diode. Howda? Light emitting diode is a heavily doped PN junction diode. Heavily doped PN junction diode. Heavily doped PN junction diode. In the next line, due to more availability of free charge carriers, when connected in the forward bias, due to more number of recombinations, at the depletion region, energy will be radiated out. In the next line, the semiconductors which have the energy gap range as 1.8 electron volts to 3 electron volts will radiates the light energy The next point, the silicon and germanium radiates infrared rays In the next line, when the forward voltage increases, then brightness of LED also increases up to some limit, comma, if voltage is further increased, then brightness will decreases. ಇದವಾ ಉದಯ್ ನೋಟ್ಸಲ್ಲಿ ಬರಿತಾ ಇದ್ದಾವೆ, ಏನೋ ಬೆಂಚ್ ಮೇಲೆ ಬರಿತಾ ಇದ್ವು ಅನ್ಸುತ್ತೆ. Finished? Draw this symbol. And also I said, what is that? Last point is what? Up to some limit the brightness will increases. After once you cross that limit, at that time what happens? It will keep on decreases. That is the last point. And the example here is which one? Gallium arsenic. Draw the symbol, that's enough. Symbol of the LED you draw. This one. So it will operate in which biasing? Only forward biasing. Next is photodiode. Next one is photodiode. Photodiode. Photodiode means here what happening in the LED, it is taken the voltage and then it is given which radiation here? Light radiation. In photodiode what happens? Nothing but everything will happen in reverse. So what happens means it will take the light radiation and then it will give the current to us. That is a photodiode, or we can say it as a light detecting, LDR also. So in the light detecting sensors also, whenever for example here LDR is there, light detecting sensor is there, whenever I am there here on that, this is a sensor here, so on that lighting is falling so that nothing will happen. Whenever I just go near to this and then I kept my hand like this, then what happens? It will give an alarm. Why like that? Why means here before light was falling, then what happened? I just kept my hand, nothing but light is not falling on that, my shadow is falling on that, so that what happens? Nothing but at that time it will trigger the alarm. That is how thief detectors will be there. The home security also they will put like that only. So and also even you might be seen in some of the movies that whenever we enters into the room, at that time automatically lights and then fans will be on. Deva Baralali light detecting sensor is there, LDR is there. Akshata, we are, everybody is laughing, no? She is just looking like this. ಏನಮ್ಮ ಏನಾಯಿತು ನಿದ್ದೆ ಬರ್ತಾ ಇದ್ದಾ? ಅಷ್ಟು ನಿದ್ದೆ ಮಾಡು. ಅದರಲ್ಲಿ ಯಾಕೆ ಅಷ್ಟು ಡಿಪ್ರೆಷನ್ ಯಾಕೆ? ತುಂಬ ಡಿಪ್ರೆಸ್ ಆಗಿ ಬಿಡ್ತಾ ಇದ್ದೆ ಪಾಪ. ಖರ್ಚಿಗೆ ಬೇಕಾ? ಖರ್ಚಿಗೆ ಬೇಕಾ? ಇಲ್ಲ, ಆ ಖರ್ಚಿಪ್ನೇ ಸುಮ್ಮನೆ ಇದೆ ವಾಟ್ರಲ್ಲಿ ಸ್ವಲ್ಪ ವಾಶ್ ಮಾಡಿ ಹಾಕ್ಕೋಬೇಕು, ಅವಾಗ ತಣ್ಣಗಿರುತ್ತೆ, ಕೂಲ್ ಏರ್ ಬರುತ್ತೆ ನಿಮಗೆ. ಚಂದ್ರು ಕೊಡ್ತೀಯಾ? ಯಾರಿಗಂದ್ರೆ ನಿದ್ದೆ ಬರ್ತಾ ಇದೆ ಅಂದರೆ ಚಂದ್ರನಿಗೆ ಖರ್ಚಿಪ್ ಕೇಳ್ರಿ ಅಷ್ಟೇ. ಇಲ್ಲ ಬೇರೆಯವ್ರ ಖರ್ಚಿಪ್ ಬಂದರೆ ಐಡೆಂಟಿಫೈ ಮಾಡ್ತಾರೆ, ಚಂದ್ರ ಖರ್ಚಿಪ್ ಬಂದರೆ ಐಡೆಂಟಿಫೈ ಮಾಡಲ್ಲ. ಅವ್ರದ್ದು ಸ್ಪೆಷಲ್ ಖರ್ಚಿಪ್. Right. Here what happens in the LDR, otherwise photodiode means it will just sense the light. If light is falling, nothing will happen. If light is not falling, at that time it will give you the alarm. Nothing but it is just based on, it is working based on the light falling on that only. So here what happens means this is a photodiode. In this will be connected in the reverse bias actually. So everything is operation is so much of theory will be there for that. Finally, we need the problem, and then for that problem we have only E is equals to hc by lambda. That's it. More than that, nothing will be there in this. Whatever the concepts we are discussing now. And also, in that also VI graph will be there. That is also little important. Now, here in the LDR, otherwise photodiode, what happening means light is falling on the junction here, depletion region. Light is falling on the depletion region. Whenever the light is falling on that, actually in the depletion region, what happening? Which are there? Electron hole pair is there, na? They already got recombined and then they have stored in which, where nothing but depletion region only. Here what is there? Only electrons. Here what is there? Only holes are there. Here electron and then hole pair is there. Whenever the light is falling on that, electron hole pair nothing but how they got paired here? Covalent bond is there in between them. So whenever the light is falling on them, they are gaining the enough energy to break that bond. Whenever they are breaking that bond, they move immediately out of the depletion region. Then what happens? Current will be produced in that. That is the main operation of the photodiode. So whenever the light is falling, already light is giving some energy. E is equals to h nu energy light is giving. By using that energy, the electron and then hole pair get separated. After separating, they will move. Whenever they are moving, obviously what will come for us? Current will come. That's it. That is the LDR operation. And whenever you see the, and also this you have to remember that it will work only in which biasing? Reverse biasing. Okay. And then here in that whenever you see the VI graph of that, see that this is the V and then this is the I. Now how the graph will be there means the graph will be there like this. Like this it will be there. So this is having different intensities. Let me take this is I1. Intensity is different, current is different. Current I am taking as small I here. So here intensity of the light which is falling on that. Here for example I have the light of intensity I1, then I am getting so and so current, so and so voltage like that. So here I1 it will be there exactly straightly actually. So here I1 and then I2, I3 and then I4 like that it will be there. So for the intensity I1 I am getting this much of current, for the intensity I2 I am getting this much of current like that it will be there. So the intensity order is, if I am just falling as a more current, more energy, at that time what happens? More current will be produced obviously. Why? Because more number of covalent bonds will be breaked. So here more energy is falling nothing but it is giving more current. The energy is directly proportional to what? Intensity here. So what I can write the order? Order of intensity is how much? Which is bigger? I1. So I1 greater than I2, that greater than I3 greater than I4. Correct? Huh? If I am just making it to fall more intensity of the light, at that time I am getting the more current. Which current? That is by the way reverse current. I said reverse bias it is working on. Then intensity I2 is little less, so only I am getting little less current. Like that LDR otherwise photodiode will work. That is a photodiode operation. Whenever the light is falling on that, it should be connected in which biasing? Reverse biasing only. Whenever the light is falling on that, it will breaks the covalent bonds and then current will pass in that. Which current? Nothing but reverse current only. Based on the intensities, current will vary. If I am just making it to fall more intensity, intensive brightness nothing but at that time more intensive light means at that time we will get more current. So here I1 greater than I2 greater than I3 greater than I4. Clear? That is about the photodiode. The main thing is you have to remember that it will be connected in which biasing? Reverse biasing. LED? Forward biasing. Zener diode? Reverse biasing. It will work like a Zener diode, otherwise it will work like a normal PN junction only. Whenever it is connected in the reverse biasing, it will work like a Zener diode and then voltage regulator. Whenever it is connected in the forward bias, at that time it will be like a normal PN junction diode. I mentioned or not yesterday that line? Yes? Like that, photodiode. Draw the circuit symbol. Draw the graph also. Photodiode or light detecting sensor will be connected in reverse bias, and when the light falls on the junction, then electron hole pair breaks the covalent bond by using that energy, and by the flow of these charge carriers, current will pass in the circuit. The light falling with the next line. The light falling with more intensity gives more current. In the next line, note point, the energy radiated in the LED is E, or energy absorbed in the case of photodiode is E. Then wavelength of that released or absorbed radiation, energy released or absorbed radiation is, what is the formula? E is equals to hc by lambda, then lambda is equals to hc by E. In the next line, frequency, how much? E is equals to h nu, and then nu is equals to h by E. H by E na E by H? E by H. Write the problem first. A photodetector is made from a semiconductor of energy gap Eg is equals to 0.7 electron volt. Then calculate the maximum wavelength which it can detect. Make it fast. 16553 is answer. 16553 Armstrongs. You got that? This much time. 16553. Lambda is equal to hc by E only. They have given an question also in the terms of electron volts only. 12400 by 0.75. Yeah, approximately also we can get 1.7. Yes, 16553, and then approximately you can get that. There is no problem in that. 16553 Armstrongs. That's the correct answer. Then next one is relation between alpha, beta, gamma. Relation between alpha, beta and gamma. We will take the common base configuration first. See that here common base configuration I have taken. Listen properly. I have taken a common base configuration. In that common base configuration nothing but that is a PNP transistor. Common emitter configuration nothing but that is NPN transistor. How to find out that is NPN or PNP? Emitter is giving the current at that time, that is NPN. More number of electrons are there. Whenever emitter is taking the current, that it will be PNP transistor. So here emitter is taking the current, and that current is given to the base and then collector here. Now from the Kirchhoff junction law, what I can write? Who is entering the junction here? E is entering, IE is entering. So that what I can write? IE is equals to IB plus IC, correct? Yes, IE is giving the current to the base and then collector. Now from this I want to get the relation between the alpha beta and then alpha gamma and then beta gamma also. For that, first of all, let us divide this equation both the sides with IC. Now IE by IC is equals to IB by IC plus 1 we will get. Now here you have to take this one in terms of alpha, beta and then gamma. So here emitter and then collector, which is absent? Base is absent. Base is absent means which combination? Common base configuration. In common base what will you get? Alpha we will get. Alpha is equals to what is the formula? IC by IE. See, immediately always you have to do nothing but you have to remember the diagram. Whenever you remember the diagrams, 3 diagrams you remember, nothing, no need to remember anything in the table. Just remember 3 diagrams, that's it, you will get the answers. So here, whenever IE and then IC are there, nothing but emitter is there, collector is there, base is absent means base is common. Common base configuration. Who is output for the common base configuration? Collector is output and then emitter is the input. Alpha is equals to what will you get? IC by IE, output by input. So here what we are having? IE by IC. So what we have to write? 1 by alpha, and that is equals to 1 by beta plus 1. Why 1 by beta? This is B and then C. Which is absent? Emitter is absent. For the common emitter, which is output? Collector is the output, base is the input. So only IC by IB is the beta, IB by IC is 1 by beta we will get. Now from this I want to get the alpha value. 1 by alpha is equals to 1 plus beta by beta. Then alpha is equals to what I can write? Beta by 1 plus beta. This is the alpha. Otherwise I want to get only beta. Beta is equals to what will you get here? Alpha by 1 minus alpha you will get whenever you solve. Send 1 that side. Take alpha as a LCM. Then beta is equals to how much you will get? Alpha by 1 minus alpha. That is alpha beta relation we got. Now I want to get the gamma. For that gamma, I will take the same equation again. IE is equals to IB plus IC. Now divide with IB both the sides. Then IE divided by IB is equals to IB by IB nothing but 1 plus IC by IB. EB which is absent? Collector. Common collector configuration. Output is emitter, base is the input. So that what will get here? Gamma directly. That is equals to 1 plus IC by IB. Which combination? Emitter, common emitter configuration. In that collector is output, base is input, so that what we got here, beta. Then gamma is equals to 1 plus beta value is how much, alpha by 1 minus alpha. Whenever you solve this, what will you get here, alpha gets cancelled, 1 by 1 minus alpha. Correct? Now I want to get the relation even for the beta, means again whenever you see the gamma is equals to how much is there, 1 by 1 minus alpha, but beta is equals to how much is there, alpha by 1 minus alpha. So can I write this one as gamma into alpha is equals to beta? Gamma is how much, 1 by 1 minus alpha into alpha. Into alpha means what, alpha by 1 minus alpha. Alpha by 1 minus alpha is what, beta only. This is what the relation between gamma, alpha and then beta. Gamma alpha is equals to beta. Clear? Everybody understood, right, everything? Yes. Write that as it is. Common base configuration. From that we got the answer. We can even get from the common emitter also. Everything we can get in each and every combination. Off cheyama.